Okay, great. Well, we might get things started then. So welcome everyone today, and thank you for joining this talk series on quantum in industry. So my name is Peter Mountney, and I'm a Royal Society Entrepreneur in Residence at UCL, and it's my real pleasure today to host an event with two fantastic speakers. So first off, we have Andrew Lord from BT. Andrew joined BT in 1985 after a BA in physics from Oxford. He's worked on a wide range of optical network systems, including long-haul subsea and terrestrial systems, including the DWDM. He is currently the head of BT's optical research that includes quantum communications. And we'll be starting with Andrew's talk first, and then following on with Ramy Aboushelbaya. So Ramy is CEO of Quantum Dice, which is an award-winning quantum company having spun out from Oxford University, and they are developing the world's first compact, completely embedded, self-certified quantum random number generator. So thank you very much for both of you for joining today. And Andrew, over to you.
Great, let's share my screen and give me some feedback when you see this, and I can start.
Yep, we can see you. And I think it's just in presenter mode now. Fantastic.
Great, okay, so I have 20 minutes, so I'm just going to hit my timer. It stops me going beyond, otherwise it gives me an electric shock. Anyway, great to talk to you guys. Thanks for the welcome, Peter. Really looking forward to this hour, engaging with you all. Really looking forward to some questions as well. So please feel free to grill me on anything that you like, preferably related to quantum. I'm going to talk about what we've been doing recently to bring quantum into an industrial kind of capacity where we can actually start to sell it, make some money at it, and trying to bridge the gap, if you like, between research and actual industrial commercial implementation. And so some of this will be obvious to you, and there'll be other aspects that you won't recognize because it'll be more general networking. And so, you know, some of it will be easy, some will be hard. But actually, the trick here is to bring two very different disciplines together. One is quantum physics, and the other one is how do you do genuine, you know, ordinary classical networking. I mean, I know there's a wide range of audience here, so some of this you're going to know well. So I don't want to dwell on this slide particularly. Suffice to say, there's a huge amount of investment going on worldwide on a range of different quantum areas at the moment. From a BT perspective, as you would expect, most of our interest is in quantum communications, that one down the bottom there, but we're also really quite interested in the quantum compute side. From a telco perspective, that's the kind of thing we could offer as a service to customers that can't afford to buy their own quantum computer in the future, but might want network access to something secure. So we're quite interested in quantum compute from a telco perspective, as well as obviously quantum communications. But we've also done work in and continuing to do work on quantum timing, because we're looking at how to build a fully synchronized network that's independent of GPS satellites. And for that, atomic clocks offer a massive improvement in accuracy compared to the current technologies. So we're doing work in that area as well, and maybe less work in the area of quantum imaging and sensing, but not zero. So we've also looked at these. We've looked at the capability of sensors to detect where our cables are underground, for example, and we're interested in looking at whether we can use very sensitive sensors to give us warning when equipment is starting to fail. So we have some ideas there, but I guess that's less kind of relevant to us. But this is the main kind of aspect of the talk today. It's around using quantum communications to help improve the security of our communication systems. And this slide here just says, it just basically summarizes security as it is at the moment. And essentially you do two things when you try to secure communications. You encrypt your data, but to do that you need a key. So before you encrypt your data, you have to get a key somehow, and you need some key also at the other end to decrypt the data. Okay, and so the question is, it's not so much how do I encrypt my data, it's more about how do I get my key to the other end so that they can decrypt it once they've got it. And how do I make sure that key distribution is secure? And that whole key distribution industry, if you like, is achieved at the moment using public key crypto systems. So you have a public key crypto system just to distribute keys, and then you use those keys to encrypt data using something different, AES, some kind of symmetric protocol. But it's this public key crypto method of distributing keys that you then use, it's that's under threat from quantum computers. It's been around for decades. It relies on factorizing big numbers, but this is something that quantum computers are very good at. And they're very good at it because of this particular algorithm. It's really famous now. I'm sure everyone's heard of this. Actually, understanding it is not quite so straightforward. But the algorithm itself is a beautiful, actually, way of using a quantum computer to very quickly find what's called this Euler period. So some fundamental property of a very large number that very quickly, from once you found that period, allows you to actually find the factors of the number. And it's actually a very beautiful algorithm that uses quantum and classical working together. Quantum gets you to the period of this big number very quickly, in hours, rather than billions of years. So it's a very, very fast speed up. And then the classical wrap around that will get you to your solution. But this is bad news, because this means that a future quantum computer will be able to crack all of our existing cryptography, at least the cryptography that's distributing keys. So what do we do about it, and when do we think this is going to actually hit, and how urgent is this problem? So, I'm sure the guys out there that are looking into quantum computers will know this better than me, but the story of quantum computer development has been rapid and probably changing almost every week. Okay, I have to update this slide pretty regularly, and in fact, this is out of date now because I see Honeywell have just launched their quantum machine. And that was I think last month or very recently. So yeah, this picture is changing, and we're seeing a huge investment and huge growth and improvement in the power of quantum computers by the month. But the question then is, well, how quickly will these get to the point where they can start to really put at risk our basic cryptography systems? Because they can't do it yet. So I've now got a slide that we've produced internally in BT to try to answer the question. I'm not saying this is the definitive answer, and in fact you'll see here a range of different answers. We're hedging our bets. It could be anywhere between 2024 and 2038 or something. What's going on in this curve? So the yellow line, horizontal line, is an assessment of how many qubits. These are proper, genuine qubits that are fully entangled, and how many of those you would need to potentially break an RSA crypto system. And then the lines that are all rising linearly are projections from where we are now to but basically making different assumptions about how quickly we're going to see growth in quantum computers. And you can see that when they start to intercept the line, that's when we're running a real risk that our crypto systems are under threat. But we're predicting, it's very, very hard to predict, yeah, and the earliest prediction there is around 2025, so that's in 5 years' time. But I mean, in my view, the amount of the billions of dollar investment going into this is going to make that happen, probably sooner rather than later. And also, I'm not sure we even know that the full extent of how that development's going, and it only needs one or two breakthroughs in the base technology to accelerate those curves. So we have to do something. We have to do something also because fiber is vulnerable. All you have to do is bend a fiber and light will come out of it. You can see a picture there of a very typical picture of bending a fiber with some red light. And you can see that the glow around the bend is where the fiber is escaping, where the light is escaping. and then you can just detect that light. You can buy a simple device, costs a few tens of dollars, and you can hack into fiber systems. It's not trivial in that the fiber itself is fragile, and so you have to be careful when you're doing it. And when I do it, I normally just break the fiber by because I'm clumsy. But people that know what they're doing here can use this sort of equipment to tap into fiber systems. Okay, so we are at risk. We will be at risk in a few years' time. And the solution that we've been looking at BT and across the industry over the last well, probably 20 years, but I've only really seen industrial engagement in probably the last 7 or 8 years. It is around this idea of quantum key distribution. So instead of distributing my key using this public key crypto system, I'm going to use a different method, a totally different method of distributing a key. I'm going to do it using a quantum distribution method where it's single photons, one photon at a time. Okay, and on the next slide, I'm just going to talk a bit more about that. But again, I'm assuming that probably this is not new to most of the people here, so I don't want to labour the basics. Just want to point you to them, and then we can go on to talk about applications. So the idea itself is okay. I send keys modulated on single photons, and the photon modulation could be in terms of polarization or phase or position, or even a combination of all of those. Some parameter of the photon, which allows me to set it up according to some basis state. I can set it up either as a 0 or a 1. But then if someone comes along and tries to hack into it and tries to measure the photon with a different basis state, they'll get a random answer. Okay, worse than that, if they try to then put the photon back and try and pretend that they haven't messed around with it, the photon is changed. Okay, and they can't completely clone the photon. That's impossible. And so you have photons arriving at the receiver that have been modified by someone that was trying to hack into them. And so innately, this system is secure if you set it up properly. Back in 2014, we did a trial with Toshiba, who were and still are, I think, very advanced in terms of the hardware that they built around QKD. And in fact, I noticed in the last couple of months they're now going to commercialize their QKD technology finally, which is very, very exciting. I mean, they're not the only ones. There are other QKD manufacturers out there, but Toshiba's very good. The boxes at the bottom of this picture are how they would implement the quantum channel, the QKD channel, and the boxes at the top are how that QKD quantum information gets used to encrypt classical data. So there we introduced ADVA, who are a well-known WDM optical transmission vendor. BT sells lots of ADVA equipment. ADVA provide the Ethernet access that many people, many companies or businesses would use in the country. And what we've done is they're integrated the quantum channel and the classical channel, so that the classical is encrypted by the quantum channel. So we've built a complete integrated classical plus quantum communication system, and that was back in 2014, just over 27 kilometers. Since then, quite a lot has happened. So the government has invested a lot into, as you know, into quantum research in the UK. They've set up a range of hubs, one of which was the Quantum Communications Hub. And part of that work was to build this. So we built several years ago now, and it's still installed, still running, a quantum field trial link between Adastral Park, which is BT's research labs near Ipswich, and Cambridge University. And the link goes through BT exchanges. So we've implemented an actual genuine commercial looking solution with QKD encrypting several 100 gigabit channels, again using ADVA's transmission data. The QKD here was provided by ID Quantique, not Toshiba, so we've now got experience with multiple QKD vendors. And each of those exchange buildings at Ipswich, Bury, Newmarket we're implementing a trusted node. So it's like we have separate QKD links with keys being basically swapped at the exchange points. There's not one long QKD system; it's multiple that are being concatenated together. And then recently we've done this trial here. So this is a trial where we've installed real commercial equipment in a company in Bristol called NCC, and we've used a commercial OpenReach BT product. And if you look at the equipment in this trial, it just looks commercial. And this was a big press release a month ago. And this now is at the point where you could imagine almost starting to sell this. It actually it's that mature. Just want to talk through very quickly through another really exciting spin-off of QKD, and that is not just using fiber, but the chance of using it through space from satellites. And again, if this sounds far-fetched, this is also getting close to the point of maturity, where we are starting to see commercial systems being discussed, and I expect them to emerge in the next couple of years or so. And here, the idea is that a low Earth orbit satellite would distribute keys to a ground station and then take those secure keys around the globe and send the same keys to another ground station, which then gives you a secure channel, which could be encrypting data that goes over fiber across the sea or whatever. But the satellite is just distributing the keys globally. And this, in conjunction with fiber-based distribution around the country, could potentially give you the way to distribute keys globally. I'm just going to, what I want to do now in the last few minutes is bring this together. Okay, so at the moment, all we can really do is do a simple QKD distribution into a business. The picture there on the far left. I've got a business, I want to connect them up together over a few tens of kilometers, I can do that. Where I think we've got to get to, and the challenge now for BT and others in the next 10 years, is to really get to the point of a quantum internet where QKD is pervasive. Okay, it's not just in my access to my buildings, but it goes through a metro network, through a core network, and through a global network using satellites, so that I can start to connect up all of the main buildings in a big multinational or corporate business. Like BP, for instance. BP might want to have all their oil rigs connected up so they can do very secure remote control. Just one example. For that, you need this kind of structure, and we are nowhere near this. So this is where so my kind of research is now falling. How do I build something like this, given that I've got the base technology? And actually, this is where the other kind of aspect of networking comes in, which if you're a quantum person, you might not be so familiar with. But how do I build normal networks, and how does quantum feed into that? And you can see on the right there a very well-known diagram of how a physical layer network is constructed all the way up to the application layer. And the physics is right at the bottom, the fiber or the satellite. But what you do is you have to build up this stack which adds protocols as you go until you finally get to your application layer, which could be video or email or something. Somewhere in there would be Ethernet. Somewhere in there will be an IP network. If you're using broadband on a computer internet, then that's going to have an IP, a layer 3 aspect to it. Where does QKD fit into those? At which layers do you encrypt? All of them? Some of them? And if you encrypt, say, at the IP layer, how do you build an IP network that carries these QKD keys? We're not really clear. So this is really kind of the next question, is how to integrate QKD into existing networks. And I'm imagining a kind of topology like this, where you can imagine the UK with some main nodes, maybe just a handful, 10 or so nodes, where you build QKD quantum distribution points between them. There may be then 2 or 3 satellite stations across the country which are taking the global keys in. And then in any local station, local area, sorry, at the bottom there, you would build more of a metro distribution into that area. And I expect probably this is going to be built gradually, and you probably fill bits in as you go. But this is going to take a good 10 years or more to actually go through this exercise. But ultimately, this is what a quantum internet, at least the beginnings of one, is going to look like. So I just want to conclude. What have I said? Quantum computers are coming. They can't crack these codes yet, but they soon will, maybe between 5 and 10 years. And then we have to do something about our cryptography. One solution is to fight quantum with quantum and look at QKD as a way to give us an ultimate secure way to distribute keys. I'm pretty excited about the role that BT's had, not that we've done this ourselves at all, but in terms of bringing together the different parts and building a network solution. This kind of the added value that I think a company like BT has. And we've been doing this now for 5 or 6 years, so we've learned a lot about the issues when you come to try and do something like that. And then finally, I've tried to show how there's still lots to do from where we are now in terms of building bespoke point-to-point QKD solutions. We've got to get to a quantum internet. Everyone's talking about it, huge amounts of investment coming from Europe, from the US, and here in the UK as well. But what is that roadmap, and how do we get from here to a pervasive quantum internet? And I've tried to give some clues about that, but I've also said, honestly, we still don't really know. Which is good. It means there's more research to do and a lot more exciting things still to come. I hope that's been useful and looking forward to some questions. Thank you, Peter.
Great. Thank you very much, Andrew. That's a really fascinating talk. Thank you. We do have some questions coming in, but I think we'll keep them to the end. So if I could invite Ramy to come on, switch his camera on and mic on, and tell us all about quantum dice.
Yes, of course. Could you just allow me to stop the video, because I think you were the one who stopped it?
Henry?
Can you see me?
Yes, we can see you.
Perfect. Thank you. Thank you very much. So I'm just going to start sharing my screen right now.
Great, we can see your screen as well.
All right, perfect. Okay, good afternoon, everybody. My name is Ramy Aboushelbaya, and I am the CEO of Quantum Dice. And I'm here today to tell you a bit more about what we do at Quantum Dice. So we are looking right now to develop the world's first compact, ultra-embedded, source device independent, self-certifying quantum random number generator. Now, there's a lot of words in that sentence, and hopefully by the end of the talk, you'll at least get a bit of a good idea about all of them. So the problem we are trying to solve really is the problem caused by the fact that the way the world works today is that it's filled with connection points. There is a vast network of connections that have made our lives a lot more convenient, have allowed us to work from home in times such as these, have allowed us to communicate across great distances, host webinars from our living rooms. But these connections, they came with problems. So each one of those connection points offers a point of vulnerability, because at each connection point, there could be a data breach. So this is not a small problem. Last year, IBM estimated that the global average cost of a single data breach was $3.9 million. Now, this could affect everything, could affect from the key infrastructure that we rely on every day, to the communications networks that we use, to our own personal private data that's now stored in so many different locations and constantly being transmitted from one point to another. Now, of course, for that reason, encryption, protecting our data against unwanted access, has become one of the most important tasks of modern day computing. And yes, I realize the irony behind using Alan Turing as the poster boy for good encryption. So any encryption algorithm out there is reliant on a basic set of primitives, a basic set of underlying infrastructure. Now, for most of the things that we use, you basically, as Andrew was mentioning, you have an encryption key and then an algorithm, a protocol that tells you how you're going to use this key. So the problem now is we're going to have to use classical communication networks. We're going to have to use a channel that you do not trust. Now, the solution around that in classical communication has been things like public key cryptography, symmetric key cryptography, so protocols such as the RSA or the Advanced Encryption Standard protocols. And of course, because these solutions don't really rely on some inherent security. They mostly rely on the difficulty of certain mathematical functions. So in computer science, they're called one-way functions. So it's a function that's easy to compute one way, but very difficult to do in reverse. So Andrew mentioned a bit about the idea of factoring large primes. So it's very easy to take two large primes and then multiply them together. To take the resultant number and then factor it is a much more difficult problem. And so far, it's such a difficult problem that it is unrealistic to expect to be able to do it with our current computational capabilities. But that is not for long. And for that reason, there are multiple different schemes for what people like to call post-quantum encryption. So encryption in a world where quantum computers are usable and can actually break what we currently use. Well, for that, of course, there's also quantum key distribution, which is a communication protocol reliant on the security features of a lot of quantum processes. And these are pioneered by companies such as, of course, BT, Toshiba, ID Quantique, and so much more all around the world, ranging from China to the US to Europe. Quantum key distribution is growing rapidly, and it's offering an amazing way to solve the problem of communicating these keys, of communicating the basic building blocks of our encryption systems. But the problem is, okay, so even if we solve the communication problem, there still relies a problem on generating these keys. So these encryption keys are generally generated randomly because you don't want somebody to be able to guess what they are. So they're constantly being changed, and they use a random number generator. So this is where quantum dice comes in. So generating random things is not as easy as it sounds. It is actually quite difficult to have an actual random process. So right now, around the world, people mostly use either what are called pseudo random number generators. And here, just from the name, you can tell that there's a problem. So pseudo random number generators are basically software-based random number generators. They take some initial random seed, which could be a processor time, it could be keyboard clicks, it could be even an output from another random number generator. And then based on some algorithm, they generate a string of random numbers. Now, of course, herein lies the problem. These algorithms are going to be deterministic because they're run on classical computers. And this causes a vulnerability. It causes the potential for what are called cryptoanalytic attacks, where you can attack the random number generation itself and actually able to break the encryption that it supports. And in the case of pseudo random number generators, there are multiple different cases, and there are multiple different situations where this has happened before. So recently, for example, in Taiwan, they had a smart ID system, and in 2013, they discovered a very big vulnerability in the system that affected tens of thousands of citizens' cards due to the random number generation that they were using. Now, this is government data, so it has a huge vector for identity theft. And all of this because pseudo random number generators are inherently deterministic. And right now, most pseudo random number generators that are being used are what are called cryptographically secure pseudo random number generators. So they are certified by certain standards body around the world, such as, for example, the NIST in the United States. But this is not a guarantee of anything. So a couple of years ago, the NIST had actually certified one specific pseudo random number generator as being cryptographically secure. And then later, researchers showed that it actually contained a backdoor. So it was possible to actually extract what the output is going to be and to use it to break the encryption that it's using for. And in fact, a lot of people accused the NIST of doing this certification on the behest of the NSA because they thought that the NSA wanted to use this backdoor. Now, of course, we'll never know if the story is true or not. But what we do know is that the NIST delisted this so-called cryptographically secure generator from its list of approved pseudo-random number generators. And so let's move a little bit from the software-based solution to what are called classical true random number generators, which are generally based on some kind of source of physical noise, some kind of source of physical randomness. So they are hardware-based. So for example, you can imagine something that's more based on atmospheric conditions or weather. And now, of course, here in the UK, you can reliably predict what it's going to be like, but maybe elsewhere, you're going to have a lot more fluctuations. But in the end, the problem with these kind of classical physical processes that also inherently, they're not random. A classical system is inherently, of course, deterministic. It's determined by the specific laws of physics that govern it. And now, for that reason, they can be easily biased. The reason why they're actually, we model them as probabilistic is because the system is so complex, has so many different parts, that the only way to model it is probabilistically. A small change in one aspect could completely change what the system looks like. Now, of course, this lack of knowledge doesn't actually inspire confidence. You're basically using this system because you don't know it, and because what's coming out, you can only model randomly. But then you have this potential for an actual hardware-based attack, for some kind of hardware manipulation itself on the level of the hardware of the system. Now, this is not theoretical. This has actually happened. So Intel spent a long time developing the Ivy Bridge processor and including in it a true random number generator, a classical true random number generator. And as soon as they released it, it was shown that you can actually attack the physical hardware of that random number generator itself and compromise the numbers that are coming out. Now, and that not only that, you can do that without the checking mechanism, that the post-processing checking mechanism that the system has, being able to detect that this has happened. And because of all of these various problems with classical hardware-based random number generators, a lot of researchers looked towards the only thing that we know to be actually truly random, which are quantum processes. But, I mean, we've known quantum mechanics for a century now, and we've been able to make good quantum processes for decades. However, getting a good quantum random number generator is not that simple, because in practice, there is no such thing as a perfect quantum system. You're going to have to use physical hardware. And when you do so, you're going to introduce classical noise into your system. You're going to introduce some classical randomness there. And as we've seen, classical randomness is actually compromisable. So how do we check for that? How do we make sure that the randomness that you're getting is actually secure? Well, there are two ways. Either you check the output or you check the process. And right now, most people look at checking the output of the generator. So looking at the numbers that come out and seeing if there's any bias or anything that can be detected. But that is problematic. And let me give you an example of how. So imagine my random process is me flipping a coin 128 times and counting the number of heads that come up. Now, the number of heads that come up are just going to obey a binomial distribution. Pretty simple. Now, what if I only do this once? I'm not really sure what if my coin is perfectly balanced, so I'm not really sure if the probability of having heads is 50% or is it biased. And I want to see if I can detect from the output whether it's biased or if it's actually perfectly balanced. But if I only sample once and actually did this, well, numerically I didn't actually flip a coin, it's impossible to tell. Can you really tell from what's left, from the left or the right, whether this is a balanced or a biased coin, which one it is? Well, let's maybe increase the sampling bit a bit. So let's do this experiment 8 times. Now, here, you can maybe kind of start to guess which one is the balanced one and which one is the perfectly balanced one and the biased one. Now, if we really want to be sure, we need to increase the number of sampling quite significantly. So if we increase it up to 1,000, now we can definitely see that coin on the left is the one that is balanced and the one on the right is the one that is biased. But this is the problem. We'll have to do this so many times. And this is an extremely simple example of an extremely simple system. And this is why looking just at the output is not sufficient. So this is where Quantum Dice's unique selling product lies. Our source device independent self-certification protocol. We do not look at the statistics of the output. What we do is we continuously monitor the actual process generating the randomness itself, the actual physical process that's creating this randomness. And we estimate how much is going to be coming from the quantum process versus how much is going to be coming from the classical noise. And then using this disk protocol, we distill the quantum randomness from the classical randomness. Now, what this does is because it eliminates the classical randomness, it protects you against the kind of hardware-based attacks that other devices are susceptible to. It prevents the silent failure problem that is very common with a lot of sources of entropy and with a lot of hardware devices in general, where you have a device that breaks down and stops working, but your system can't actually tell that happened. Because of this continuous online live monitoring of the quantum process itself, we are capable of preventing this kind of failure. And because our system is simple, doesn't require single photon sources, single photon detectors, or any kind of complex setup, it can actually enable us to go for a completely integrated design. And of course, when you go completely embedded, this allows for cost efficiency. Now, this means that we can take this system from where it's currently at in the lab to the hands of a consumer. And thanks to, in fact, this integrated design and this cost efficiency, this is not just going to protect the server rooms of Google or Amazon or IBM. This is going to protect your cell phone. Now, these are big claims, but where we are right now is we currently have a discrete component prototype. So we have a basic implementation of this protocol, and this implementation is done in a large-ish device that's producing numbers at an output of 8.05 gigabits per second. And the first step is to take this discrete component prototype and miniaturize it into the size of a USB stick. This creates a hardware component that can then be integrated into the kind of server-style systems that we see in communications networks or in banks or in cloud services providers. But that's just the first step. The real end game is to take this device and go completely embedded. Because our system is based on optics, the challenge here is to take the optical components as well as the electronic ones and put them on the same chip. And thanks to incredible advancement in optoelectronic fabrication, this is feasible. And this is where we aim to go completely embedded and create an on-chip low-cost QRNG. That's not just designed for things like servers or high-end enterprise solutions, but smartphones and consumer Internet of Things devices. Now, just to give you a note that random numbers are not just important for encryption. Random numbers have a wide range of uses, ranging from scientific simulations, so things like drug discovery, things like simulating physics, simulating astrophysical phenomena, to pricing financial derivatives. So this has become one of the biggest uses right now in non-encryption uses for random number generators. So this is very important for like pricing options, futures, where you have to do a lot of modeling of stochastic and random processes. And speaking of which, it's also important for non-financial stochastic modeling, things in economics, things in elections, for example. So if you don't have a proper source of randomness, the results of all of these things can be heavily biased. And we have seen this with the failure of a lot of systems that are designed to try to predict the future by sampling or by picking a particular subset of data. If you don't do this properly, you can end up with disastrous results. But of course, this is what Quantum Dice is claiming. How are we planning on actually giving people the confidence to know that what we are claiming is actually true? So this is why we have partnered up with the National Physical Laboratory here in the UK. And we are working with them on a QRNG hardware standards project. So this is a project that's funded by Innovate UK for the next 3 years, where we'll be developing a standard for QRNG hardware in order to certify not just the randomness of the output as other randomness standards that exist out there, like the one provided by NIST in the US. No, we want to certify the randomness of the process itself. And thanks to working with the MPL, who are, by the way, working with not just us, but other QRNG manufacturers such as ID Quantique, Cas Quantum, or other companies right here in the UK. In fact, working with them is going to provide third-party validation that what we are claiming that a device can do is actually what it does. And it shows in a quantitative way the advantages that going for a quantum random number generator is going to be beneficial and going to be more secure than going for a classical one. And let me just leave you with the idea that the threats that QKD is going to protect against are coming, but they are still future threats, as opposed to the threats that QRNGs are protecting against. The problems with random number generation is not something that is going to start happening once we have a quantum computer. The problems with the current random number generation is something that is happening right now. And at this point, I'd like to thank you for listening, and I would love to answer any questions that you may have.
Great, fantastic. Well, thank you very much, Ramy. That was a great presentation. If I could ask Henry and Andrew to join us back again, and over to you, Henry, for the Q&As.
Yeah, so one of the first questions which touches on QKD was, what's the issue with sort of increasing the RSA key size up? Is that a cheaper method than relying on sort of early stage quantum computers?
I mean, for me, You just need more qubits, and then you'll break it again, and you reach a point where RSA struggles with just the implementation size in terms of just the amount of energy it takes, and a lot of these things don't work very well if you keep scaling them. We're trying to do with QKD is stop the ongoing battle of kind of continual competition against the hackers and the implementers. What QKD does is solves the problem. So yeah, you could keep increasing your RSA key and cope with the implementation each time you have to do that. But I think what QKD is offering here is an ultimate solution for those systems that really don't want to have to keep going through that cycle again and again.
Another listener asks, are there sort of other ways to fight quantum with quantum, so other alternatives outside QKD?
Yeah, I should have really talked about post-quantum cryptography, shouldn't I? I didn't have the time, but obviously the classical way to do this is to find a better algorithm than RSA, an algorithm which maybe quantum computers or even classical computers can't solve. One of the well-known ones is something called lattice codes, and they're currently under a big competition in NIST in the US to make open source an approved NIST solution, and I think there's several I think have been shortlisted. I think there's still about 2 years to run in that competition, and yeah, that's one solution. So another thing we've been looking at is something called a physically unclonable function, or a PUF. Now a quantum PUF is a little chip that gives you is impossible to copy. Okay, so it has something inbuilt, innate in it that if you send it a challenge, it will give you a unique response. And I think they might have applications in parts of the network where QKD is too big, or like a sledgehammer. There's parts where for IoT or a driverless car or something, or your phone, you might want something that's not quite so it's not so heavyweight, and I think PUFs may well offer an opportunity there.
Another question for you again, Andrew. PKI provides identity as well as a secure secret key exchange. Can QKD supply the same?
No, all of the QKD demos that we've done have had classical authentication, but once the authentication's done, QKD takes over. So it's not backward looking. So because QKD uses a random number generator, hopefully from Ramy, then once that authentication is sorted, keys are then not related to that authentication. So you just need to do it once. Okay, and for sure that authentication currently proposed is using PKI, which is one of the schemes in the competition from NIST. But again, these PUFs may well offer another route for doing that authentication. But I think, and a lot of the problems that we're having getting full accreditation of QKD is around that authentication. We're having very deep discussions with National Cybersecurity Centre in the UK to work through their issues around authentication. So it's a deep subject, and that's a very good question.
So a question for Ramy. What kind of physical implementation is Quantum Dice using for RNG?
Yeah, so our random number generation is based on optical circuits. So we have an optical circuit that's the source of our quantum noise, and then there's a post-processing circuit that's electronic. So when I was talking about when we were going to miniaturize, so the challenge was how do you combine an electronic and an optical circuit on the same die? Now there's been a lot of advancement in that specific topic in research, and especially in fabrication techniques. And in fact, some of the biggest foundries out there, some of the biggest semiconductor foundries, are looking at doing and providing an optical integration stack for their fabrication processes to allow for mass manufacturing of these kind of devices. So basically what we use is a laser source and some waveguide beam splitters as well as photodetectors. So a very simple implementation that relies on very commonly found optical components.
So is the scale of your demonstrator sort of like tabletop size, and you're sort of like scaling down, or
so right now it's actually about living room table size because I have it right here. But the next goal is to get something a little bit smaller, a little bit more compact, and hopefully that's going to be sent to Andrew. And then the next step after that is to go completely embedded.
Yeah.
So
Peter wants one as well.
I guess I wanted to ask a general question. how do you see the sort of the landscape to getting towards a sort of like quantum internet? How long do you think we have the like building blocks in place? Because we're sort of, there's all these sort of disparate research groups and different startups all working in slightly different pockets. And how do you sort of bring that together into one sort of communications network?
Yeah, I think there's a bit of misunderstanding when different people use the word quantum internet, and that's unfortunate. And I think what I mean is something very prosaic and simple, and that is just connecting boxes together and have a key distribution around the country. But probably what people really mean by it, especially in academic circles, is actual entanglement distribution of qubits, where you can start to interconnect quantum computers. And for that, you said, as you say there, there's a whole, Henry, there's a whole load of other things you need. So you need a quantum repeater, you need quantum memory, and these are things that are all being worked on in the UK and other places at the moment. But that feels, to me, you probably know better than I do here, feels longer away. So I think what my role is really to build the more prosaic, pragmatic quantum internet, and then that will hopefully gracefully evolve into something where you start to take out the trusted nodes and put in quantum repeaters. Maybe you start to extend the length of QKD by using clever techniques like device independence, where you can have intermediate nodes that you don't have to trust. So there's ways to get close, but ultimately we are going to need this whole new generation of components.
Another question about the trial you ran using QKD. Why did you use sort of separate QKD connections between points, multiple points instead of one between the two sites?
It's too far. Yeah,
Yeah, sure.
It didn't work. So there's different QKD technologies. Some go further than others. To go further, often the QKD boxes need more clever stuff, and often that means that stuff is more sensitive, delicate, not so easy to keep calibrated for long periods. And so it's a very interesting challenge at the moment. Do I want to build myself a cheap and cheerful QKD box that just does a short distance, or do I want to go for a much longer, like 100 or 200 kilometer type distance, in which case I've got to really throw everything at it, and that's a lot of ingenuity then. Another issue is, do I want my QKD to work on the same fiber as my classical data? That's a very, very big question, because the classical data messes up the quantum channel very easily. If I can build a quantum network where the classical data is somewhere else, not on the same fiber, that makes life a lot easier.
So a question for both of you this time. In order for fully commercialized application, how does the speed/clock rate of the current QKD QRNG system compare to the classical system? Would you say that it's currently sufficient? Let's start with Ramy.
So it depends on whether you're comparing them to pseudo-random number generators or to a hardware-based device. So compared to pseudo-random number generators, of course, they're slower, just because a pseudo-random number generator is basically as fast as your computer can go. But at the same time, it's not very much secure. So it's going to have to be a cost-benefit analysis of which one is more important to your use cases. So for us, so the device that we are putting onto the market is going to be faster than the Q1s that are already out there. So there is no currently available quantum random number generator that has a higher bitrate than the one that we're developing. And we're aiming to try to go as fast as possible, basically. But what we are putting out there when we speak to potential customers, whether they are in classical encryption systems or whether they are developing QKD systems, our bitrate is more than sufficient for these use cases.
Another question for you, Ramy. What's stopping physical tampering with, I think it's disks? Could it be tampered to making the output not perfectly random?
So nothing is going to be perfectly secure. So as much as I would like to say that once you use quantum, that's it, everything's going to be perfectly secure, that's just never going to be the case. What we aim to do is basically close as many loopholes as possible and mitigate any vulnerabilities that exist in a system. So DISC, our source device independent self-certification, it mitigates the vulnerability associated with tampering of the physical source of randomness. Now, this doesn't have to be tampering that's basically actually manipulating the hardware on the chip itself. So other than what was shown with the Intel chips, There was also tampering that was done, for example, via electromagnetic flooding. So you use some RF frequency that you use the signal to flood a random number generator and impact how it produces things. So things like that will be mitigated by our device. Now, of course, if you manage to actually access the physical hardware of the device and tamper all the components on it, then you're probably going to be able to affect it. But that's going to be a vulnerability that we're going to have to work to find another way to overcome. And there are always proposals and research to overcome as many as possible. But you close one, another one's going to open. The goal is to get better, and perfect is, and not let perfect be the enemy of the good, basically.
So I think for my final question, someone asked, is there, how do you get into this particular industry, or whether either of your teams are looking to hire people in this area?
I think it's a pretty good time, isn't it? There's a lot of Innovate UK funding, a lot of EPSRC projects. So outside of industry, and even in companies that are involved in Innovate UK projects, they're all hiring at the moment. I'm currently leading a project, QKD, an Innovate UK project looking at free space optics and QKD. And I know that many of the companies in my project are all having to hire because they've been successful. So I hire occasionally, not at the moment, but have hired recently, actually. Ramy, I can't speak for you.
So for us, we are actually actively hiring. We're looking for photonics and electronics engineers. So if you're interested in getting into quantum, please get in touch, and hopefully we can set something up.
Back over to you, Peter.
Great. Well, it falls to me just to say thank you very much for taking time for everyone for joining us, and thank you very much to Andrew and Ramy for two fascinating talks. So great, thank you very much, and thanks everyone for joining.